I want to teach you about deep Gaussian processes. So quite a few of you asked questions, like I just got a question of what happens if I model a non-Gaussian, non-stationary time series. How can I do that with Gaussian processes? Lots of things you want to do with Gaussian processes when things aren't Gaussian. And deep Gaussian processes are a way of making things not Gaussian processes because they're functions of functions. So a deep Gaussian process basically is a setup where you have a missing pen. I've lost all the pens. Oh, here we go. I've been hiding them down here. F1 of F2 of X, where F2 is a Gaussian process and F1 is a Gaussian process. So it's a composite function. And of course, you can keep doing this. And that gives us the depth. So I think you'll see results from a model like this. 1, 2, 3, 4, 5. Yep. A 5-layer deep Gaussian process where we start with some x, we put it through a Gaussian process, and then we put it through another Gaussian process, put it through another Gaussian process, put it through another Gaussian process. Now this means everything's not Gaussian, because even you put it through one Gaussian, a Gaussian going through a Gaussian process is not a Gaussian. You can sort of mentally think about, well, it's in general not a Gaussian. Why that is, because let's say I do it in one dimension, then I'm mapping a Gaussian through f of x, and that's a nonlinear function in one dimension. I'm likely to get some sort of function like that, yeah? It's not going to be Gaussian again. It's only Gaussian if I use a linear mapping, yeah? So if f of x is w times x, and x is covariance sigma, this is covariance w sigma w transpose, right? Okay. Now, so the first thought I had in this area was really inspired by talks by Jeff Hinton, I think back in 2003 or something, or even earlier, when he was first talking about deep models and he presented to us at Microsoft. And I wanted to do, as soon as we did the GP-LVM, oh no, it must have been later than that. It was after I'd done the GP-LVM paper. I thought, oh, well, I could try and do deep GP-LVMs. And this was the first attempt at it. It's sort of hierarchical GP-LVM, we called it. And the idea was, remember what we briefly mentioned before, the case where this is time. So we had the GP-LVM, so some latent space here mapping to some stick figure walking or something like this. And then we want to put a temporal process over here. We want to say this is going on as something in time. And what I said was, one of the things we did was put an f of t prior over here, over this domain, which is a Gaussian process. So it'd be like a two-dimensional Gaussian process. You can sample those. They will give you like continuous smooth paths that overlap on each other and stuff like that. So that's one way of doing dynamics, and it provides a simple hierarchy. The input space of a Gaussian process is governed by another Gaussian process. But by stacking them, if we can do that once, we can do that multiple times. But ideally, we want to marginalize these intermediate variables. What we're really saying is something like f1 is a function of x1, and x1 is a function of x2, and x2 is a function of x3. And now we've got to treat these things probabilistically. So this is the composite function type approach. But because there's uncertainty in all of the outputs of these functions. So to do it probabilistically, it's perhaps not correct to write it down like this. Or actually, though, what we did for this first model is we did just write it down like this. And at the top level, we had time. And each of these was a Gaussian process with no noise in it. If you put noise in, it didn't work. It just increased the noise level. But they were noiseless Gaussian processes, and we just did back propagation through the whole model. Gradient descent across the whole thing. So I didn't think that would work. Well, in fact, what we did initially is we fitted these models greedily. So we took data sets, and we fitted the model at this low level to the data set. And then we put a model on top, and fit that model to the latent space, and so on and so forth. This is how they did these original deep models with restricted Boltzmann machines. So this is a result of that type of model, where we initialize by, we've got two people and they walk together and they high five like this. And the idea is you want one latent space for each person. So this person here perhaps is being coordinated by this, and this person here is being coordinated by this. And then you've got, once you've trained that, initially you just train that, then you train a second latent space that has as inputs these two. So this is two-dimensional to like 100-dimensional, and this is two-dimensional to two-dimensional. Why 2 dimensions? Because I can plot them on a graph. There's no particular reason. I couldn't select the dimensionality just so that we could visualize things. And you can see what we have in this model is the point A is here, and point A is also here, and point A is also here. So this guy is mapping in a nonlinear way to there and there, a 2D to 4D mapping, and then it's mapping from this 2D space to that guy and this 2D space to that guy. Yep. So that kind of worked okay. And we also did a model like this, which I sort of mentioned briefly earlier, where we do that within a subject. And the idea here was we can do really nice models of humans walking. They work really well, actually, and they're very popular in areas where people have low data. People have done tracking with this, animation. There's some beautiful videos of people using GP-LVMs to construct very realistic looking animation using only very little data. But there's this issue of if someone is walking and they wave, and you've never seen a wave before, now you can't disconnect this arm. It's all correlated by the GP-LVM. So the thought was here, well, model the arms separately and learn a good model for the arms from lots of data, perhaps, and model the legs separately, and then model a shared model for the upper body. So you take these latent spaces and put them into another latent space, and do the same for the legs. And then it turned out it's best to do the abdomen separately. So this is like the body. And then put it all together at some top governing node. And then if you were running this at runtime, and we did this paper for BMVC where we did this, and you discovered that the arm wasn't fitting to the model, you just cut this connection and model the arm as just some random separate thing, yeah? No longer correlates. So we call this idea backing off because it's related to ideas in language. So language processing, you have these like n-gram models, and you try the largest n-gram you can try. Like if you're trying to build a model of words, we try predicting, like n-gram means how many words do we predict in a sequence. And then we check whether we've ever seen an n-gram model, so a sort of fourth order. So if I say Gaussian process latent variable, that's a 4-gram, and I can predict the next word should be model. But if I say hippopotamus latent hummingbird cat, what's the next word, right? So you try the 5th order model, and then when that doesn't work, you drop down to 2nd order, 4th order, 3rd order, 2nd order, and predict with those. So trick used in language processing, and that was the idea. We were going to be able to do that. Eventually, that you would try this high order thing here, and then you would cut bits off to try and do the tracking or whatever you were doing. So that seemed to work okay, but the nice thing about that is I still have the 7-year-old demo, which I'll now try and show for you. It worked this morning, so let's hope it works now, of this working. So, this is MATLAB. We haven't recreated this in Python. It would be a lot better if we did it in Python. So, here's the stick man, and here's models of his right arm, left head and left arm, and his right leg and his left leg. Now, we've combined 2 motions here. So there's a walk motion and a run motion. And what we did is, we forced all these guys to share the same models for walk and run, apart from at the top level. So at the top level, we switch in a different model. So each of these is a Gaussian process latent variable model. This one is governing these 6 dimensions here. This is governing the right arm. So, for example, I can make his right arm move, yeah? This one is governing the head. Do you like Gaussian processes? Yes. This is the left arm. And these are the right and left legs. So you can see how now we can do sort of independent things like, you can do the cha-cha-cha, whatever, we play football. But all this stuff is just taken from a walk and run model, yeah? Now, interestingly, it clearly doesn't want to match the abdomen together for the walk and run. We told it, model abdomen together, but it's actually just put them in separate spaces. These guys are all somehow linked. So look, this is the walking arm movement. But we also see the running arm movement. Just as we move between walk and run, we bend the elbow, yeah? And then we get a more exaggerated movement. So it's found some commonality. And so we can interpolate between walk and run emotions in the arm. But with the abdomen, it's like, no, these two are nothing to do with each other. So here's the abdomen for walk, and then here's the abdomen for run. Yeah? So it's decided they're two separate things, and it's put them in here separately. The legs we can do together now. So the inner ring is a walking leg. Oh, and you can see now it's controlling actually these two, so that the dots move around below. Whereas the outer ring is the running leg. And if we can interpolate again between. And it's put the inner ring inside the outer ring, like you might hope, yeah? The upper body. So there's the running motion. And here's the walking motion, yeah? And then, of course, if I go all the way up the top here, and if I'm good about following the right path... Oh, I made him walk backwards, sorry. So at the top, this is constrained now. What was important in this model is there's a top-level dynamical model, Gaussian process prior over this thing, right? So that's why you see only evidence in these areas. What happened is we built this model by stacking it, and then we tried this backpropagation through the whole model. Now, if we left in noise, you're allowed to put noise in GP-LVMs, so we put noise in at each level initially. If we left that noise in, if we allowed that noise to move, it would just grow to dominate. So basically, the reason is, when you think about it, these guys overfit by saying, get off. I don't want to be controlled by anything above. So we're adding extra parameters here, but those parameters constrain the model. So one way of thinking about this is this here is obviously a two-dimensional manifold that is mapping into this space, which is 6-dimensional, that is mapping to this space, which is 1, 2, 3, 4, 10-dimensional. So it's mapping to this space, which is 4-dimensional, which is mapping to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12-dimensional space. But implicitly, when I move on this space, I'm moving on a two-dimensional manifold in that 12-dimensional space, yeah? So that walk constrains everything to live on a two-dimensional manifold. And the run, alternatively, constrains everything to live on a two-dimensional manifold. Just a different one, yeah? One that sometimes they're overlapping, but sometimes they're distinct. So if you just allow the model, the way the model overfits is by switching on noise. Get rid of those constraints. And then it replaces this stacked hierarchy of GPs with just GP-LVMs at the lowest level. And that's how it sort of overfits. So this is a funny thing, because putting in these extra parameters is constraining the model. And it overfits by getting rid of them, because they're constraining things to lie on lower dimensional manifolds. Does that make sense? That's another odd sort of thought. Normally you add parameters, you think you get more modeling power. Here, you restrict the domain of the model by adding parameters. So we had to take out the noise, and then we just did backpropagation through the whole thing. And that's in effect a map solution for all these latent spaces. And it worked quite well, but we didn't, and I really like this model, but we didn't do much to follow it up because we had to impose this structure. So we couldn't learn this structure. We said, maybe arms are two-dimensional, maybe legs are two-dimensional, maybe the upper body is two-dimensional, maybe the run and walk are two-dimensional. Why did we choose 2 dimensions for each of those things? Because I can show it on a screen, yeah? Not because we really believe those things are 2 dimensions. And we had no way of selecting either the dimensionality or the connectivity, how these things are connected. So we can do it for something like human motion, where it's all sort of obvious what the conditional independencies are. But any general data set, if we want to do this thing, we were stuck. OK? So that's the way things lied for some years. I guess 6 years. Okay, so back to the presentation. Whoop. It's annoying, I seem to have to restart this presenter every time I switch away from it, so we always go back to the beginning. Sorry about that.
Excuse me. Did you train that just with one sample for running and one sample for walking, or you had several?
No, that's just one sample for running and one sample for walking. Interesting story. I was working on this when I was visiting Raquel Urtasun at MIT, and you've just reminded me about this. So there's only one cycle of walk and one cycle of run. So there's not even one sample. It's like one pace of walk and one pace of run. The thing was, if I started adding more paces, the model was not really handling it very nicely. It was doing something and it was doing okay, but it wasn't really clear what was going on. Well, I started by adding more paces, and Raquel said to me, why don't you just do one pace? Sometimes it works really well, because she's an expert on human motion and uses GP-LVMs. We'll just do it with one pace. So I did it one pace, it looked great, so I said, okay, we'll go with that. But you know, my feeling was, while it was a really extraordinary model, there were things sort of missing, so we didn't sort of follow it up. So inducing variables are the key here. So I'm going to go through the inducing variable stuff again, because actually it's quite important, and I think you heard it once, but I'm going to do it with my slides now rather than James's slides. It's important enough to hear twice. So as I sort of said, that these sparse approximations date back to work by Chris Williams and Matthias Zager, Alex Smoder, Peter Bartlett, Lehel Sharto and Manfred Opper. This is Chris Williams, Matthias Zager and me, Ed Snelson and Zubin Garamani. We sort of looked a little bit of these. But we're back to this variational perspective of Michalis Tsitsias. So as we've already seen, this is an augmented latent variable method, and it's followed by a collapsed variational approximation. What do I mean by a collapsed variational approximation? I didn't really show you the details. I'm kind of going to show you them more this time. What happens is that we lower bounded this likelihood type term, and then we integrated over these augmented variables. The integration, the second step, which we can do as an actual integration rather than variationally, is why it's a collapsed variational approximation, because it's called collapsing rather than sustaining that latent variable out. And that type of collapsed variational approximation was first proposed by myself and Nat King in 2006 and widely ignored. With James Hensman, we did a lot better job of explaining how general that approach is. So I could see it was kind of worked quite well in some models. James really saw how general that was. So that, I think that's a very nice paper that James led at NIPS a couple of years ago. So these inducing variables, remember them from before. I'm dropping F at the moment for this. So we want to build these models over Y, but we integrate out, we introduce the augmented inducing variables, which is how we're going to store the information. And we can do that because they integrate out. And then we introduce this particular structure, P of Y given U, P of U. Right? And the thing we did yesterday was show how we could lower bound P of Y given U, and then do this integral and get a setup which required an order m squared computation rather than m cubed. And of course, I'm now introducing the F we had yesterday, that we assume that relationship is through F. It's not directly on Y. So you've seen this sort of thing before. But do stop and interrupt if any of this is unclear, because I think it's important stuff. So very often the likelihood P of Y given F factorizes across the data in this form. Other factorizations would be okay if it factorized for small subsets of the data, but we'll consider the case where it's factorizing across the whole data. And what I want to do is focus on the integral over F. So you see on the right, what's the change I've done there? Can you see what's moving around? The df on the right-hand side is jumping inside the P of U. Yeah? So we're assuming U is given. Okay? We're leaving the P of U outside. And we're assuming U is given, and we're focusing on the term that if we integrate over F would become P of Y given U. Yeah? So F is our latent variable. And what we do here is we make a variational approximation. So the variational approximation is this one. This is the same one we saw yesterday, but here I'm just saying it in general. So this is slightly different to the way we introduced it yesterday. This is Jensen's inequality with a variational distribution. So this is the standard way of introducing variational approximations. We did it slightly different yesterday. We swap the integral and the log, but we do so while simultaneously introducing a Q of f. Now how do we introduce the Q of f? Where did Q of f come from? Came from the same place as the mythical elbow plot and the mermaids and everything else. Fantasy land. It doesn't really exist, but what we do is introduce it like this. P of y given f, P of f given u. So this is the standard variational trick. We want the log of this. We're going to do Jensen's inequality again. Jensen's inequality allows us to swap the log and the integral around to give us a lower bound. That pen's not working very well. df. So I've introduced Q of f here, but when I introduce the log, I keep this Q of f with the expectation. So I sort of force this to be an expectation. So this Q of f here, I think of it as being over here, and I move this outside the log. So that's a modified sort of Jensen's inequality, and I'm allowed to do that if this thing is positive coefficients, which it is because it's a probability distribution. If it can go negative, I'm not allowed to do that. But I'm allowed to do that on Jensen's if this is positive coefficients, and therefore I end up with this Q of f, bring the log inside the Q of f, P of y given f, P of f given u, df, Q of f. Now, this is actually the way Michaelis originally derived this bound, and what he said, getting to this point is standard, he said, what if I set Q of f equal to P of f given u? And if you do that, Q of f and P of f given u cancel. And you get exactly what we saw the other day. Now, what's the missing term here? So you can show, we're missing that KL divergence from yesterday, but what you can show is that the difference between log P of y given u and Q of f, sorry, the integral Q of f log P of y given f, P of f given u, Q of f df is equal to the Kullback-Leiber divergence, but I'll write it out as the form of the KR divergence, log Q of f divided by P of f given y comma u df. Why is this so? Well, it's reasonably easy to see. Sorry, have I got that wrong way around? I'm subtracting that, I've got this upside down, is equal to minus this. I think? No, it should be, yeah, so I've got the KL divergence the wrong way around, haven't I? So, sorry, let me correct that. So I'm just doing a sanity check as I go, and the sanity check didn't work, so I'm assuming I've got this the wrong way around. Either that or I'm insane, which could be possible too. I always forget which way around KL divergences go, but I think that's right. So this is the Kullback-Leiber divergence between P of f given y comma u and Q of f. I mean, another way of seeing these Kullback-Leiber divergences is you can see them in this way. This is the log of these two things, so it's the log of P of f given y comma u minus the log of Q of f, right? So the log of P of f given y comma u minus the log of Q of f. Yeah? So that gives us some function which over the entire line of f will vary like this, depending on whether q of f is larger or smaller in its log space than p of f given y comma u. Okay, so that's not a number, but now we take the expected value of this number under the distribution q of f. And you can prove that that will always be positive. So it's some measure of the difference between these things. It's the measure of the distance between them under this distribution. Okay? So you can see how it's measuring distribution dissimilarity. And it has lots of information theoretic interpretations. So, of course, you should also be thinking, where's he going with that? Well, if we set P of f, Q of f to P of f given u, P of f given u, remember that from yesterday? This is the compression between what we're choosing to store about the world in u, if we're only choosing to store information about u, and what's stored in the world about knowing y and f. So it's another way of deriving the bound from yesterday. Is that clear? Maybe even clearer than yesterday. Okay. And that's what Michaelis suggested doing. But what does it do on the interesting thing, and this is the way Michaelis looked at it, is he said, I've got this now, I'm just going to set that to that, and that's going to cancel with that. You get the same result, which we had yesterday, that log p of y given u is greater or equal to the expectation under p of f given u of log p of y given f, because this guy and this guy cancel and disappear. Yeah? So we're left with p of f given u log p of y given f. Now, the other thing, of course, is if p of y given f factorizes, it has this form. So this is our lower bound on the true p of y given u, which is like going to be our pseudo likelihood observation. Now for Gaussian likelihoods, if you work this thing out, because if this is a log Gaussian and this is an expectation under p of f given u, which is also a Gaussian, the log Gaussian gives us these terms which are all quadratic in f. So we get all these little bits and bobs here, but we also get this term here, the expectation of f squared minus the expectation of f all squared. What is that term? Anyone please? So it's the variance, isn't it? It's the variance of f. Yeah? Now, that term appears because I want to write this term here. Really, when I write out that quadratic form, if I write out the quadratic form y minus f times squared, which is what's inside the log, yeah, when I take the log of the Gaussian, I get a y squared minus 2yf minus, plus 2yf, no, minus, I was going to put a minus up there, plus f squared, right? And I take the expectation of this, expectation of this under p of f given u, expectation of this, which is just the expectation of that, and then I've got this expectation s squared. But now I want to write this term, sorry, the purple's a good pen. Purple's a nice colour too. But I want to rewrite this like this. So I want to rewrite this as y minus expectation of f all squared. That doesn't lead to this though, that leads to this, but with expectation of f with the square outside. So how do I fix that? I fix that very easily by minusing that in and, well, minusing this and adding that. Yeah? That allows me to refactorize that in this form. That's the origin of the trace term, the penalty term. Yeah? This expectation is under p of f given u. What was the trace term, the penalty term? It was simply the variance of p of f given u, wasn't it? And that's that term there now. And that allows us, but this thing is now in the form of a Gaussian. If we unlog it, if we exponentiate it, this is in a Gaussian form. So that's what led to yesterday's form, which I didn't sort of do the details of Gaussian in y given a mean of k fu k uu minus 1 u, comma sigma squared I, times exponential of the minus 1 over sigma squared trace of, so this was product over all these, trace of kf f minus kfu kuu minus 1 kuf. Yeah? That from yesterday we had that. This was the penalty, and this is the sort of looks like a likelihood term. That just comes from exponentiating this. That gives me the Gaussian, but then taking the expectation. What's the expectation of f under P of f given u? It's just the Gaussian process mean of the posterior. KFU, KUU minus 1. This thing's popping up all the time, you know. It's the mean of a Gaussian process conditioned on u. Yeah? We keep, that's our test predictions, that's our everything, that's our lives. And this one here is simply, as someone said, the variance of f under P of f given u. And of course, but it keeps appearing, it's the product of all the variances. So here this trace term is just taking the sum of the diagonals. The sum of the diagonals is the product over the diagonals if you take the product outside the exponential. So this is just the result of taking the product across these likelihoods. Okay? Simples. So I think I've just done all that. So the way I've written it here is I've defined CI to be, each of these is a CI. Exponential to the variance here divided by sigma squared. So I'm missing a 2 here, aren't I? I'm defining to be CI. I've defined that variance to be QII, and then I'm defining the, that thing to be CI, just so that I can write this thing, which is the lower bound on the whole likelihood. So now I've reintroduced P of u. Yeah? So P of u is the thing I left outside. I said we were going to focus on integrating over f, and I've left u outside. So I've reintroduced P of u, and now we have a Gaussian with the mean of expectation of f, and the expectation of f under P of f given u is that. So note this is linearly dependent on u, and u is a Gaussian distributed variable. So it's trivial to do the marginalization. What is the marginalization in this case? If I tell you that, I mean, it's just that multivariate rule again. So if I want to do, so C is not dependent on u. So that's why I've rewritten it as C, constant. The only thing that's dependent on u is the mean of the Gaussian distribution for P of y. So we're saying P of y, so we're saying y is equal to KFU, KUU inverse, sorry. Yep, that's right, yep. Times u plus sigma squared plus epsilon, where epsilon is sampled from a Gaussian with 0 mean and a variance sigma squared, and u is sampled from a Gaussian with 0 mean and covariance KUU, because that was our prior covariance for u. So what is the form of the marginal likelihood for y, please? Shout it out.
Gaussian.
Gaussian, yep. Mean, 0. Covariance. Say
KFU.
KFU, yeah. What next? KUU inverse times what? KUU, yeah. Times what? Oh, we're not transposed yet. Now we need this thing transposed, right? So times KUU, so this thing transposes KUU inverse transposed times KFU transposed, which is KUF, and that's symmetric. So one of these KUUs cancels, and we get a covariance of the form of KFU, KUU inverse, KUF, plus what? Sigma squared. Isn't your life easy when you do Gaussian processes? That was a multivariate, high-dimensional, potentially infinite-dimensional integral. Wow. Nice. Okay, so that's the marginal likelihood. That's called the collapsing stage. If you sustain, you could also do an EM algorithm here, right? You could do an EM algorithm where you look at the posterior of u given f, and you keep that. Okay? That's the uncollapsed variational bound. Doing this integral like this is collapsing the variational bound. It's doing one of the steps analytically after making another bound. And that's what that other paper was about, when you can do that. We've got this paper, Gaussian processes for big data, and that's all based on not collapsing this bound. That was something that James spotted. So look at that. Yeah, okay. Yeah, look at that. That's what we've just done. So if you'd not done that properly, you wouldn't have got your certificates. Okay, but I've introduced again the C's, because the C's are still there, right? So we were just ignoring the C's. And so what we end up is the lower bound is of the form of this thing, which looks like some low-rank Gaussian process, and this thing, which is the sum of the log penalty terms, this trace term. So what it is it's the difference between the variance of the true KFF, the diagonals of the true KFF, and those that are coming from U. And basically it goes to 0 if U equals F. So we talked about that yesterday. Okay. So having done that, yeah, what did I want to say now? I wanted to move on to this, yeah. So just that last point there is really about the fact that if you want an approximation, you can drop these C terms. So this here is a lower bound, and it's a lower bound because of these log C's, right? Clearly it's not a lower bound if it's a log probability, because it can't be a lower bound if these are both probabilities unless they're exactly the same. So if we drop these log C terms, that's what people do in this DTC approximation, you get an approximation. Okay. And that's called the projected process approximation. It's called like 100 different things, proposed by several different people, but it's much better interpreted as this variational bound. So what's this to do with the Bayesian GP-LVM? So the GP-LVM is a probabilistic nonlinear dimensionality reduction algorithm, but because we're maximizing over x, we can't choose the dimensionality of x, because increasing the dimensionality of x will always give us a better likelihood, right? It's like adding parameters to the model. So the only way you can choose the dimensionality is something like cross-validation or something like that. What we really want to do is integrate over x as well, give it a Bayesian treatment, integrate it out. But that looks crazy. I mean, it's just so you look at that and you think there's no chance you're going to be able to integrate over x. Because when you look at P of y given x, you've got a Gaussian with 0 mean and this covariance here over ff plus sigma squared or whatever. How does x appear in KFF when you start writing out the Gaussian? Back to purple. If I look at what this looks like, I get this term half y transpose KFF inverse, sorry, KFF plus sigma squared inverse. So I'm going to put a prior over x, and I need to find a prior that when multiplying by a covariance which has x in a pairwise sense, which may be all right, but has now distributed these x's all over that matrix in some crazy way that, you know, we can write down a 2 by 2 and everything else. That seems really impossible. You're thinking, okay, what can we do about that? So what we want to do is integrate out this x. So we'd like to put a prior over x. We've already done the prior over the mappings, and we want to put a prior over x as well. But that integration is intractable. Now, we can always say we'll do a variational approximation on x, okay? And the variational approximations always have this form. So we wrote down one earlier in a slightly different way, and this KL divergence actually is not between the prior and the posterior, it's between, sorry, between the true posterior and the approximate posterior. It's between the prior and the approximate posterior. You can always write them in this form, or to do that you basically have to take a term from here and put it here. So this is variational inference. We need the expectation of P of y given x, log P of y given x, under some approximate distribution. Doesn't matter what the approximation distribution is, this will still be a lower bound. But if we look at what the log P of y given x is, it's this form. And we've got to take an expectation of this. So we need to take an expectation of this guy in here under Q of x. If we could do the true posterior of Q of x, that would be an exact algorithm. But we don't even want to do that. We just want to do, like, oh, let's just say Q of x is Gaussian. Let's just say it's Gaussian and try that. Do this expectation. We can't do it because of the inverse. We can't take that expectation because of the inverse. That's what that's saying there. And also, of course, the determinant. Yeah, forgot about that. Okay, but let's go back to that collapsed variational bound. And the thing Michaelis spotted. So I sort of think, if you look at it at this point, and I'm tempted, I want to integrate out P of u. Let me integrate out P of u. No, don't integrate out P of u yet. There's a P of f giving you comma x in here. And if we wanted to do things, actually I think this should be a Q of x. And just in general, any distribution, Q of x here. Or P of, sorry, no. It's P of x because we're looking at the marginal bound here, right? So this is all true. Now we apply the variational lower bound to the inner integral. So we take the P of u out, and we wait. We wait to collapse the bound. You can't collapse the bound yet. If you collapse the bound and then try the P of x, the expectation under P of x, it doesn't work. But we're going to keep P of u, hold on to P of u, and actually do this integral under P of x now. And what we get is this form. We can get this variational form for it, which looks like the standard variational bound from above. Once we've done this, this turns out to be tractable. Why is this tractable? Because the difficult term here is this log of Gaussian, where x is appearing under the expectation of f. This is just, if we say Q of x is Gaussian, this is simply the KL divergence between two Gaussians. And we can just look that up on Wikipedia, not even from 4 years ago, just today's Wikipedia. But what we need is the expectation of this log Gaussian here. But because we've waited to collapse, because we've not collapsed u out yet, we can do that expectation because it's the log of this, right? So the log of that is going to be y minus kfu, kuu inverse u. So transpose y minus kfu, kuu inverse u, divided by sigma squared. When we multiply this out, y transpose y, we don't have to worry about, minus kfu, kuu inverse u, let's put y transpose at the front, half in front of there, half in front of there, plus u transpose kuu minus 1, kuf, kfu transpose kuu minus 1 u. Where does x appear in this equation? It only appears in kfu and kfu transpose kuf, or kfu, kuf, kfu. These aren't inverted anymore. So in order to get this expectation, it doesn't appear in kuu. Only z appears in kuu. I didn't say z had any probability distribution over it. Why should I make it have a probability distribution over it? It's a variational parameter. It's something I just optimized to improve the model. That appears in the inverse. If we had to put a prior over z now, we'd be in trouble. But we don't have to. And what we actually need to be able to compute is the expectation of kfu under a Gaussian distribution and the expectation of kuf, kfu under a Gaussian distribution.
It also appears in the trace, no?
Yeah.
For KF.
Yeah, it appears in the trace in a similar way. Thanks, Maurizio. Yeah. So in a trace, you end up having to compute similar things. And also, sorry, you're right, Maurizio, we need to do the expectation of KFF from the diagonal, from the trace. Okay, so these expectations are, what are the form of them? They're the expectation of k of xi, comma xj, perhaps times k of time xi, comma z, times k xj, comma z. That's the quadratic one. And they're the expectation of k xi, comma z, and the expectation of k xi, comma xi. Under Gaussian distributions, they're just matrices. So, these aren't always computable. They're the expectation of kernel matrices under Gaussians. Which covariance matrix do you think they might be computable for? What covariance matrix? Exponentiated quadratic, because then it's just the product of two exponentiated quadratics. It's an exponentiated quadratic again, and we can do the integral from minus infinity. We know the answer to that. So in code, we call these the C statistics. I say C because I call them psi, but Michaelis, I think, invented that they were the C statistics, and the Greeks say C, I think, for that letter. But that's really confusing. If you start pronouncing things like that, then how do you pronounce this letter? P. Yeah, but if you pronounce that P, what's the difference between that and that? Let's call it pi and psi. Okay. So that works. That also works for the linear covariance. For the linear covariance, this is just the expectation of x transpose. It works for the polynomial covariance. It works for the product of a linear and exponentiated quadratic. And there's even a hope that you could maybe do importance sampling or something like that. Once you've done that, you then have to integrate over P of u, which is also tractable. Woo! Okay. So, what can we do with that? Well, this is a Gaussian process latent variable model, and we're integrating over x now. And the first thing you can do with this is you can sort of recognize that actually if you've got a 6-dimensional x, what you've really got is some sort of multiple latent variables. Each of these y's is now dependent on multiple x's, right? But let's focus in on one of those y's. And this is just one Gaussian process. Okay? All we have is the inputs to the Gaussian process being shared. Now, this Gaussian process is dependent on, well, why have I put W in there? Yeah, so W, if we're just assuming we're doing integrating over, we're back to the linear model again. We have two sets of variables. We've got X, which we're integrating out, and W, which is the same dimensionality. Now, they always appear as an inner product, as we've seen before. So you've got this sort of weird duality where what we can do is this thing. So what I want you to think of doing is we put a prior over x with some variance, and we've got a standard spherical prior over w, which is how we derived the GP-LVM in the first place. But the prior over the x has some particular variance. But what I want to do now is give each of those x dimensions their own variance. And what we'll do is we'll learn this variance. So this means that if you think about what we're saying is we have a latent space. Oh dear. With a latent space x, we're mapping from this latent space with wx to some observed space, which might be a stick figure, y. And what we're doing is I'm suggesting putting a prior that is diagonal covariance. So it can decide that this dimension here isn't being very useful. It can start reducing that. It can drive one of these values to 0. Or alternatively, it could go in that direction. It might not, but it could. It can decide to use less. It can decide, not much going on there. Let me try and shut that down. Okay? But oddly, that's very equivalent to this model. What have I done now? I've switched x and w. So these two models, one's saying this and putting a spherical prior on w. The other is saying, no, 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 no. Spherical prior on x, but I'm going to scale the columns of w when mapping to y. Yeah? The two things are mathematically identical. But actually, when I think about these models, I tend to flip between the points of view in my head because sometimes it's convenient to think in one way and sometimes it's convenient to think in another way. So the fact that they're mathematically identical, and it turns out that it's also similar for Gaussian process models. So Gaussian process models sometimes have these covariance functions called ARD, which switch off input dimensions. And the same equivalence is true for those covariance functions. So this is an example of an ARD covariance. So we can think of priors over alpha over each. So each column of W is scaled by alpha. Or we can scale the columns of X by alpha. Now in these ARD covariances, it's actually what you've been fitting. What we do is we scale also the columns of X by a diagonal matrix A. So this is normally just the distance between the 2 points, but here it's the scale distance. So we also have this duality for this model. We can keep the prior over the latent space spherical, but allow the length scales to vary along the dimensions, or we can keep the length scales constant. So in the Gaussian process case, what's going on now is pretty much the same thing, actually. We've got some field of Gaussian process, and we've either got sort of isotropic length scale, the length scale is the same in every direction, and then we put a prior in this space which is diagonal, yeah? Or alternatively, and totally equivalently, we have like a long length scale in that direction and a short length scale in this direction, and then a prior that is spherical. Actually, it's good to think of both these points of view depending on what you're doing. But they come to the same thing. You're trying to select dimensionality. So that's what we do, and these are known as ARD priors. And this means we can do things like select the dimensionality. This is a famous data set, the oil data. It's known to be two-dimensional. And this is a fitted model from code by Andreas and Michalis, which has selected the dimensionality to be 2. It's not just 2 either. We see that there's 2 dimensions. One is it's using massively. This is this direction here, the non-linear direction. It's using a lot of fluctuation in the length scale. The other one, it's using very little. Now, if it's using very little, it doesn't mean it's switching it off. What it means is, equivalently, well, it's working well here. What does it mean? That the function is broadly linear in that direction. So either from that point of view or from the point of view that it's actually focusing down on a very small section. As you look at a smaller and smaller section of the RBF, you get pseudo-linear functions. So the model's not even just selecting for switching off dimensions, it's saying that this direction is broadly linear. And this direction is highly non-linear.
You see a large variance in that direction. Like
yeah, because it needs to take, so this is why flipping between the points of views. These are both equally valid points of views. And even though we really fitted it with an isotropic covariance and then scaling the variance, I prefer to think of this example, an isotropic variance on X and changing the length scales in the directions. I prefer to think of this example that there's some isotropic covariance going on, and then what it's fitting is a very narrow prior on X. In this direction, it's getting a lot of non-linearity. That's the long direction. But in this other direction here, it's basically getting linearity. And the other directions, it's just switched off totally and replaced them with noise. So this model is initialized with 10 latent dimensions. It chooses 2 and says 1 is linear and 1 is non-linear. And interestingly, the data, so these are all different flow. This is called the oil data. And these are just different regimes of flow of oil data. And they separate along the non-linear direction, broadly speaking. This is about the best visualization of this data I've ever seen, by the way. Seriously, and I've visualized this data a lot. It's a really good visualization. It makes a couple of mistakes. There's a sort of green dot near the red here, but it's separating broadly across one dimension. So that was the result from the original paper.
When I've seen the prior that you give different covariances for each variable, is usually to achieve some sort of sparsity.
Yeah.
Do you do that here?
Yeah, so that's what we're trying to do. We're trying to achieve sparsity. But we don't know that it's going to happen, oddly, and we haven't done any theoretical work to show why these things go to 0. you know, we started thinking, oh, it'd be great if they went to 0. And they do. But we didn't know that was going to happen. We don't have the theory. Normally, to get sparsity, you wouldn't just be able to do a Gaussian prior, would you? You'd have to say, I want to do a spike and slab prior. So I want a prior like this. So I've got Gaussian plus delta function. That's a sparse prior. Or this horrible L1 prior. It's not a good Bayesian prior. Fine for people doing map stuff, but it's not a sparse prior. It doesn't have anything sparse about it as a probability distribution. It's the exponential thing. It's just a heavy-tailed thing. Why is it not sparse? Because the posterior is never sparse. But it's used a lot to obtain sparsity, so we could do L1, potentially. Or a Cauchy distribution.
Maybe it's the same effect you get when you do relevance vector machine.
Yes, but that's... Yes, so the relevance vector machine is genuinely sparse, and Mike Tipping did a load of nice work showing why this happens. There's this trade-off between whether to model with the noise or whether to model with an additional bit of nonlinearity. And it must be something like that. I mean, obviously there's some effect that makes this thing happen, and it's an effect we hoped for, but we didn't know it was going to happen. I'd find it difficult to prove. So we need to get Mike Tipping and Anita Fowle out again to prove it, because they proved it for the relevance vector machine. So we iterate for long enough and we get these things switched off. So I think that's pretty amazing in the base case. It's automatic dimensionality selection in a fully probabilistic, nonlinear latent variable model. And I don't think, there's no method that competes in this domain. I don't think that's too broad a claim. So, have I gone backwards? How did I do that? Okay. Oh, did I just include that twice or something? I've done something weird there. Look, I included that twice. Okay, right, now, what I want to do now is switch briefly to a bit of a demo. Well, no, the ongoing demo. Where has it gone? Any key to tidy up? Is that doing anything? Here we go, yeah. And I've got the other window over here. Then move it across. There's my mouse. Playing with his mouse like a madman. There's the mouse. So this is the same automatic dimensionality reduction with a data set of Brendan Frey's face. Actually, it looks a bit better when he's smaller. So it's a 20 by 28 pixel face. And if you ever watch the video of him doing this, he spends half the video sort of pouting at you and half the video sort of grimacing at you. So these are the first 2 dimensions it's picked up. And the main movement in that direction, whether it's a pout or grimace, is him turning his head. So he's doing all this thing like that, yeah? So, of course, what we can do is this requires a lot more than 2 dimensions, but we can switch to other dimensions and see what's going on there. So here we see he sort of is moving more into the camera and out again. And it seems to be separating. Oh, I like this one here. This is where he gets angry. But then, of course, that's an unusual dimension, right? So that doesn't exist. That only exists. He did that very briefly in the data. So we can extrapolate into new data regions. So I've pinned him in that pout, I don't know, this, whatever he's doing with his face, in the 3rd and 4th dimension. But now I'll try and make him do things that he didn't actually do. So he never shook his head in reality on that dimension, but we can now make him shake his head. Yeah, I like that. So these are all things he didn't do because he only made that face briefly. But we've captured that rotation and we can combine all these things together. I think that's pretty wild. Of course, if you go too far into this, it starts to get... Oh dear. Yeah, the main lesson you learn from this is never put a video of yourself online as a data set for people to model. Nowadays, Brendan's a respected scientist, and it's very bad for me to be playing with his face in this way. Okay, so let's see what in this dimensions things were going on. Okay, so this looks like a lighting variation, yeah? It's sort of broadly speaking just a shade variation. It's not doing much to his head. And then at some point, I think as if I start going to like 8 and 10, those dimensions are broadly speaking switched off. I don't think we ran this model properly to convergence because it was a larger data set. So I don't think they're 0, 0. But this will just be a very linearly sort of, yeah, very small variation. It'll be linear. It'll be very linear, this stuff here. You can see that if I go outside the regime of the data, it continues to extrapolate, showing that it's very linear. So it's got a bunch of little linear directions.
Where is the panel at the bottom?
Oh, it's not working very well. This panel at the bottom allows me to, this is some code that I wrote that we haven't modified, allows me to move latent dimensions like that. Yeah. So you can see, actually, I should be able to move him in this there. Oh. So that should update him. Did that update him? Oh no, it just went backwards. Maybe the code set, so it's just showing the position of the latent dimension. I thought it did update. There. If I move that, it should move that, yeah. So it's moved that latent dimension. I don't know why it's not working up there. If I move this here, it moves that latent dimension. So we should see, he changed a little, right? Yeah? So that gives you an idea of how much these other latent dimensions do things. That did virtually nothing, yeah? Because those are the ones with the smaller coefficients. So we gave it like 30 latent dimensions, and from memory, I mean, we'd have to get out the plots, but it's using mainly, for nonlinear it's using fairly few, and then for linear it's using quite a few more, and then they start to fade away. Okay? Any questions at that point? I'll tidy that up.
Another question, just like to check if I understood some of the things you said. So you can just pick some dimensionality and try to optimize, and some of those alphas will be driven to 0.
Yeah.
They will pick.
If you optimize for long enough, yeah.
They pick dimensions for you, basically.
They pick dimensions for you, yeah. I mean, it sometimes takes a lot of optimization to get them all the way down to 0. But yeah, broadly speaking, yes. So Gaussian process dynamical systems, so this is now we get to do the proper Bayesian thing by putting a Gaussian process prior. We can put a Gaussian prior over this latent space, we can put a Gaussian process prior over this latent space. That first thing is just diagonal covariance Gaussian. And as soon as we came up with this, I knew that this is what we wanted to do next, but Michalis was busy with other things, and I had to wait till Andreas Damianu, a PhD student, started with us, and he started working on this and started building up these models to allow us to do what our target was, which is deep GPs. So this is a stacked 2-layer Gaussian process, which was the first step on building these deep GPs, because we wanted a Gaussian process in, Gaussian process out. So this allows us to do time data. So the input to the latent process is time. Now, let me see if I can find, I think I've only got video of this. So, you know, dear, I should have found this before. I'd forgotten that this PDF browser doesn't let me see the video of that. Deep Gaussian, there's only one way I know how to find this video, and that's through another video. So the video that I'm looking for comes up as a recommended video when you click on this video. Normally. Oh, used to at any rate. So where is it? Damn it! Oh, this, by the way, this paper here, style-based inverse kinematics, that was the first application of the GP-LVM. That's a cool video, but it's the GP-LVM. Oh no, 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 no. That's me when I was a long time ago. Was it here? Ah, damn. Okay, I can't see the video. What I wanted to show was a video by Andreas Damianu, which does interpolation for HD video. Let's see. Gaussian process. I think it's called Melissa. Oh. Okay. One last check. I'm just going to check the. Okay, looks like I can't get it. Sorry, it was a video that Andreas did, which is interpolating HD video. So that's amazing because, well, it's amazing to some people because what we did with that GP-LVM is we fitted it to HD video, the raw pixels. So we're talking million-dimensional feature spaces. And the reason you can do that, you can always do this with a GP-LVM. So we're talking P of millions, and the frame size was like hundreds or thousands. And the reason you can do this is because when you look at the likelihood, it depends on this term only. Trace of that. That's equivalent to saying y transpose k inverse y, sum over j equals 1 to p. Another way of writing this is trace of inverse k times y transpose. Y transpose is an n by n matrix. If it's made up by 10 billion features, it doesn't matter. You can pre-compute y transpose and then just use y transpose in your learning. And that's a trick we used to do interpolation of HD video. So we took video and then we cut out half the HD video and filled in the remaining pixels. So you can regenerate pixels from HD video. And we also took out segments of the video and then interpolated across the segment. Oh damn, I particularly like the dog one, which was somewhere. Oh, I'll just have one other little look here. Andreas. He doesn't use his name, I think.
Cool dog without a.
Cool dog. Videos. Let's click on videos. Yeah, damn it. It was recommending it with alongside the deep Gaussian process. I'll have one little look finally in my GP-LVM. Ooh. I might have it. Patience. Copy. YouTube. Hey! Right, I'm watching it here, right as we speak. So, this is HD video. And what you see up here is when it switches to red, it's reconstructing. Or it's in test data. When it's white, it's showing you the training data. So that's reconstruction in the red, yeah? Now, it does a bad job at reconstruction when she moves her head a long way. It's like when the worst job it does at reconstruction because, oh, sorry, not for this thing. This one's okay for doing the interpolation. But there was another variant of that video where it does a bad job at reconstruction when she half of her face is missing. So we did a variant of that. That's trying to interpolate between things, but there's a variant of that which hopefully is this one. where we move half her face. I think is this video here. Oh no, that was the same video. Was it? I9T. Okay, I don't seem to have the other video listed in there. So we can interpolate this HD video, and we can also sort of cut out half her face and reinterpolate that. No, we should be able to see other videos, sorry, but once we're just on Andreas's little account here. So I've watched that. Oh, so here's the doggy. So it watched video of this doggy running. There's the training data, and then it generates video of the doggy running. And this is all being generated by Gaussian processes. So that's an entire HD video being generated by the process. And there was one other, I thought, but it doesn't seem to be visible. Now, one of the things I want you to notice on that doggy video is that he's a bit ghosty. He's ghosty because when it starts generating data, look at his tail, he's ghosty. Now we use the periodic covariance in the time space to make him keep running, yeah? But actually you get a bit of ghosting effect, and the reason you get ghosting effect is because it doesn't understand about pixels being neighbors. So it doesn't understand that a leg movement like that to that is a smooth transformation. What it sees is a leg there, and then it sees a leg there. And it knows it has to go smoothly between those two legs. And the way it does that is to ghost a leg in. So it ghosts one leg in and the other leg. I can't bend my arm that way. Ghosts one leg. So the leg is supposed to be in the middle, but the smooth transformation is to put two ghost legs. Because it doesn't understand that a leg between those two is a smooth transformation, because it doesn't know about pixel neighborhoods. And the correct fix for that would be to pre-process the video with blurring and stuff like that. If we were real computer vision, we could fix that up and do even more realistic stuff. But we were too busy trying to push on to do the next thing I have to show you, which is manifold relevance determination, which is really something we're building on a lot now. So, oh, it's annoying when I have to go through these things again. So manifold relevance determination is structure learning with one GP. And this came about because it's work originally with Carl-Henrik Eck, my PhD student, who was in Manchester at the same time as Maurizio. And what we wanted to do is we wanted to combine two data sets together. And the way we were trying to do this, I guess we did it independently of other people, but other people have suggested similar things, is to build GP-LVMs like this. So the first paper was, someone did this with a GP-LVM. They said, okay, I'll just have one latent space generating two data sets. But I find this very dissatisfactory, because it says you've got to build a latent space which has to know everything. So if we generate myself and Maurizio with the same latent space has to do Maurizio and me, and some of those dimensions which may only be relevant, so Maurizio has glasses, I don't have glasses, so the glasses dimension isn't relevant for me, but it's relevant for Maurizio, yeah? And so you kind of want to be able to separate the things that we're shared about, we're both brilliant scientists, you know, we like Gaussian processes, in a shared space, and then separate the things, you know, that are private to us. Maurizio lives here, I live in the UK, that sort of thing, in a private space to us. So that's unsatisfying, and Carl-Henrik and I wanted to work on these type of viewed data, and we sort of said, well, let's try and build models that are a bit more like that. So we've got some sort of shared information and private information. And we did this with the GP-LVM, and we actually set it up so that some of the spaces were private and some of the spaces were shared. But we had to decide how much space to give to everyone at the beginning. We had to say shared space 3-dimension, private space 4-dimension, you know, and then try and model the data like that. And actually it worked pretty well. It worked, we did it okay, but I tell you what, the state of the art, so we didn't do all the computer vision stuff. So let me, oh, I'm not going to be able to find that video either. There's some really good stuff on this. Have I got it? I see him out. That's Victorian. Cedar and Victorian. So these guys in Oxford took this one step further. I'll just choose one of their videos at random, see if it's any good. So this is cars tracking. So, ooh, yeah. Oh, it comes up in the wrong place. So in this case, the guy, he did this shared view, which was a silhouette of the car, and another view, which was the picture of the car, and he used these two views to fit shapes around cars. That's not his most impressive thing. Maybe it's his, maybe the CVPR one isn't the best one. Let me move this on here, so hopefully the video will come up on the right place. So they've got 3 papers basically using this model. And he actually gets all this stuff to work in real time by running on GPUs. And he's really optimized this stuff incredibly well. It's standard GP-LVMs. Here we go. So he's got a silhouette. This is what Carl-Henrik and I were trying to do, but he just did it much better. So this is the latent space, and the shared space he's generating is one is the silhouette and one is the pose. So some information is private to the silhouette, because there's a whole shape of the guy, and then some information is private to the pose, because the real pose has got all the 3D information, whereas the silhouette's ambiguous. And the idea was, well, can we now put in a silhouette and say, give us the pose, or give us the ambiguity across the poses? And this is what Carl-Henrik and I were trying to do, and we did do it to some extent, but this guy knew all about computer vision processing stuff, and he's done it really nicely. He's actually got a company doing this for feet, I was being told. So he's got a company doing it so that you take a photo of your foot, and then it works out the shape of your foot using this model, and then it shows you a picture of your foot with a shoe on it, the right size shoe. It gives you the right size shoe, so you can buy shoes online. And that's all done sort of real time with GP-LVMs. This is maybe another video here. I think one of the cars video. Let's try M-player cars. So this is even without, this is with him setting the dimensionality of the shared space together. So this is like trying to work out the 3D shape of a car given a picture, given a car behind a tree. So he knows the shared space of the 2D and the 3D shape of the car, and he's fitting the 2D shape to a car behind a tree, and then that's giving him what he thinks the 3D shape of the car should be. So if I look at one of his other car videos, it will show something else. Let's see. This is Ian Reed, and I'm not very good at pronouncing Victor's surname, so apologies to Victor for not mentioning his surname. It begins with P, and it's sort of Eastern European. So there's another variant of the same thing. This one is actually a sort of SUV. So these models seem quite powerful, but you have to select the dimensionality. Now what, with Carl-Henrik, and this is going to be annoying because I keep having to move. In fact, I'll just use events, I think, because I keep swapping between the PDF and the demos, and I keep losing. Well, with any luck, I'm not sure if when I go full screen this will appear on the right screen. It often fails to. How do I get it full screen? I can't even see how I get it full screen. Okay, well, I'll just show you it on here. So the shared GP-LVM models multiple views. A few other people have looked at this. Carl-Henrik and I did it in 2008 and 2007. Gail Lean and Colin Fife, Arto Klami, and Sami Kaski, and the original sort of ideas for this turn out to be these battery factor analysis models by Tucker in '58, which Arto and Sami dug out. So CCA is a special case of this. But what we do now with our shared GP-LVM is we take this model, which originally has the latent variables all shared, and we allow separate mappings to the two spaces, yeah? And we force them to share latent variables, but we allow them to scale those latent variables differently. So one of the views can decide which latent variables to use, and the other views just could decide a totally separate set. It decides independently. And the hope is that they'll choose to share some. So does it work? Well, we've got this example from the Yale faces, which I may have up already. Okay, I do indeed have it up already. So here's a face, This is those ARD parameters. Now, what are we doing in this case? So, just to talk about the AL face data briefly, it's a series of faces with different lighting conditions. And what we'd like to find, what we do is we take two faces which have the same lighting, but are from different people, and we present together. And then we do that again, with different people in each case. So the private space should be, for each case, moving across the different people we use. And we use 3 different people in each space. The shared space should be the lighting variation. So we want the shared space to be just the lighting movement, hopefully, if it picks everything apart. And what we see is it's shared 3 dimensions, the first 3, and the others are all private, right? It's either they're blue or red. So we expect these spaces, 5 and 7, or 8 and 10, to be about identity, and we expect 1, 2, and 3 to be about lighting. So where's my latent space? So we started with 1, 2. And let me just check. I can never remember whether which of the spaces we're visualizing. 8 and 10. 8 and 10 should be about identity. So we should see 3 clusters of people in 8 and 10. Come on. So it's just thinking. Because it's MATLAB, you see, it's slow. I must, yeah, my computer is currently upset. The mouse has stopped moving. So last time this happened, I closed it and opened it, and that fixed it, didn't it? Do you think that would work again? Try that one more time. Of course, it doesn't seem to mind being closed. Okay. No, let me... I don't really want to unplug it. Okay. Oh. It's unhappy. Is it going to be happy again?
We can have a break if we want.
Yeah, that's probably a good time to take a break. Should we take a break?
Yeah.
So we want to take a picture. So let's find the right spot and take a picture.